Good news is if you're good on the spec, then you should only just keep working a few problems and you're probably good. Okay? It'll be the same idea we had on test 1. Okay, last questions about the lab this week. Okay, let's look at EAS. EAS is our most common mechanism for aromatics, although there will be a couple of others. The ring is a nucleophile, the H is replaced by the electrophile. Here's a generic reaction shown here. Let's look at the mechanism for this. Using a generic electrophile, just like an alkene reaction. Okay, we have 3 alkenes. Okay, it's aromatic, we know all that. It's delocalized. It's less reactive than a standard alkene, but it will react. In some cases, we may need to have a catalyst where we do not with an alkene, but it will react. We'll talk more about it. Pi electrons attack the electrophile just like we would with an alkene. We get the bond made to the alkene. Okay? Of course, there's an H there. We get carbocation. Nothing new from alkene chemistry. This is called your sigma complex because we made a sigma bond to the electrophile. Note that that carbon is now sp3. Sometimes this may be called a tetrahedral intermediate because it has a tetrahedral carbon now. Note that it's not aromatic because it's sp3. That carbon no longer has a p orbital. But this cation is resonance stabilized. We'll look at the resonance below, very important. From there, in organic 1, like when we were doing bromination, we attacked the Br, we had back bonding, but maybe we had a cation. If bromide added here, or if nucleophile added here, or some type of base added there, it's really not a good. Some folks use base. I would say nucleophile. Some type of nucleophile added to the cation, you might get this product. That would be an addition product. And the pi bond's now gone. We don't get addition products with aromatics. Instead, what happens here, and this is what's new, but it's really not nothing very crazy. Instead, a mild base takes the H, and the electrons move in to put the pi bond back in, and we have the aromatic system restored. So the aromaticity is maintained by this fast beta elimination here, which looks like the second step of maybe a E1 elimination. Yeah? And that gives us overall a substitution reaction where the H has been replaced with the electrophile, and some type of mild base has taken the H, and this is the outcome instead of an addition reaction. Okay. Now, this is not aromatic, but it is resonance stabilized. Very important to be able to show resonance of the sigma complex. Here's the same structure drawn down here. We can do resonance structures. Pi electrons over, cation here, pi electrons down, cation here. So there's 3 resonance structures of the sigma complex. Here's your hybrid. Hybrid is a blend of all these 3, right? Now sometimes with your charge, it's just shown as a single positive charge, sort of shown as it's implied that it's delocalized. If you want to put partials, we know we have a partial plus here, and a partial plus there, if you want to show the partials. Sometimes in the hybrid, the partials are not shown. But what we do know is that thing is positively charged. It has a single positive charge, whether it's delocalized or not. Need to be able to show resonance structures. As we move forward, there'll be additional resonance structures. For example, if we have things on the ring, we may be able to do additional resonance structures. We'll be looking for that. Those will be very important to not only tell us about two things, reactivity, and also where will the electrophile go relative to an existing group. All of that will be explained by resonance structures. So, to look at this, why do we not get the addition reaction? Well, look, either way you go, you get the sigma complex. From there, we could either get the beta elimination to give this product, we know that's what happens, or I said maybe you could get an addition product, we know that does not happen. Well, you just need to be able to explain exactly why not. Well, since this is higher energy, in that higher energy, it's not aromatic. Lower in energy. We typically say the transition state leading to the lower energy species, the transition state is going to be lower. So that's what I'm showing here. So here it is. Which way is the water going to run? It's going to run downhill. So it comes here. To get here, you'd have to go a higher transition state, and that's why it doesn't go that way. We have another pathway leading to the aromatic product, the substitution product.
If we wanted that, we just heat it up really high, or we would need a catalyst.
If you wanted what?
If we wanted the...
If you wanted this one? Well, you're never going to be able, how are you going to, even if you supply heat, why would it still not go to the lower pathway? Now, if you put so much heat in here, I mean, you might, but think about it. Why would it, even if you put a tremendous amount of heat, why would it still avoid the lower energy pathway? You have to think about how you might do that. In the end, you're going to get this down here. If the reaction was just hugely exothermic and hugely high temperature, you could see how maybe it's no longer selected. Typically, we get aromatics. Question. Given two different EAS reactions, why would one occur faster than the other?
Resonance. More resonance stabilized.
Anybody?
More resonance stabilized.
What's more resonance stabilized?
The formation of EAS that has more stability. So
Okay.
you would have,
Louder.
like, you would have more resonance stabilized on one EAS reaction, and that should be the favored
But
one.
what's more resonance stabilized?
The sigma complex.
Why? Okay. Why the sigma complex? Why are you looking at that?
Because if you like
What's
if
the
you-
rate determining step in the EAS mechanism? Two steps: forming the sigma complex, and then beta elimination to give the aromatic. Which one's rate determining?
formation of sigma.
Right, forming the sigma complex. So, two EAS reactions, which would be faster? The one that had the lower rate determining step. How are you going to lower the rate determining step?
When you just have more resonance. It's gonna
Stabilize the
have
sigma
lower
complex. The more stable it is, the lower the rate determining step, right? How can you stabilize the sigma complex?
resonance.
Resonance. It already has some resonance. Well, there may be cases where it may have even more resonance because of substituents or something. Okay, in the end though, the first question you should have focused right there, right? Why would one reaction be faster than another? Well, rate determining step, that's why. If you want to talk about the rate, I would focus on the rate determining step. That's a pretty cool name, isn't it? Rate determining step. Thus, the beta elimination would be known as the fast step, compared to the rate determining or the slow step. Of course, if you brominate just cyclohexene, we know from organic 1 you get the addition reaction. Okay? Not with aromatics. Okay, let's look at specific electrophiles. Halogen. Most common being chlorination and bromination. Using the elemental halogens. Here's a non-reaction. Benzene reacted with bromine to get bromobenzene. Forget about that for now. Plus what?
Plus HBr plus reformed.
Plus HBr, right?
Yeah.
That's the fate of the other bromine. And we do lose an H, right?
Yep.
So there's a bromine to account for, and there's an H to account for. Sounds like it might be HBr. Okay? Now, this reaction is slow. If this was cyclohexene, it would react instantly. The aromatic system reacts slower. The electrons are busy doing some resonance. Typically, you need a catalyst. A Lewis acid catalyst. Okay? Everybody knows what a Lewis acid is, right? Most common Lewis acids are like FeBr3. Note that the halogens are typically consistent. If you were doing chlorination, you'd probably want to use FeCl3. Lewis acid. We'll talk about this over here. The first step of this is, how does the catalyst activate the reaction? Well, which step is the slow step? Forming the sigma complex. But the sigma complex arises through reaction of the aromatic with the electrophile. And there's a transition state there. We can somehow make this more reactive. Another way is we can make the bromine more reactive. Then the transition state leading to the sigma complex would be theoretically easier. How can we make the bromine more reactive? Reaction to Lewis acid. What's the definition of a Lewis acid? Accepts electrons. Accepts a lone pair, electron acceptor. Yeah. It accepts the electrons from the bromine. Okay, what's going on here? Your transition metals like iron, which is the main one we're using here, we'll also use aluminum. Your transition metals have empty d orbitals. And the empty d orbitals can accept electrons. Okay? Your transition metals tend to be electrophilic with those empty d orbitals. All right? So what am I doing? I'm adding to the d orbital. What does this give? This gives bromine now added to iron. Okay? There's 3 bromines there. I'm just going to show it all condensed. Charges though. This is now minus, because if you count electrons, it now has 1 more. Okay? You should be able to see that. What's the charge of the bromine here? Only 2 lone pairs charged.
Positive.
Positive. Now we have polarized this here. Now the benzene ring will attack this bromine. Electrons attack, kick that off. How do you make oxygen a better leaving group? Protonated. But what does that cause the oxygen to become? It becomes positively charged. A positively charged oxygen is a better leaving group. Here, the bromine leaves the bromine. How did we make this bromine a better leaving group? We made it a positive charge by complexing it with the Lewis acid. Now this bromine's like, I can get some electrons back. It pulls on this bond. We get some polarization here through the complexation. So we activated our electrophile. Now this reaction, the transition state is lowered, leading to what? Well, it looks like, the way I have it down here, it looks like I pulled electrons down. Down, okay, leaving plus up here. Electrons down to go attack the bromine. Made bond to bromine. Other guy kicked off. Cation up here. Plus what? Well, the leaving group was this here. This could have been FeBr4 minus, but I showed one bond out. Here's your sigma complex. You should be able to show resonance structures of that. I'm not going to do it. What's the next step? What's the next step?
FeBr4 capital D
There's
hydrogen.
an H here. We've got to remove it. Fast beta elimination. What removes it? Okay, right here. Now, this is a sigma bond. What happens here is iron is not happy. It's like, okay, BR, I accepted you, but now I'm going to reject you. These electrons are moved away from the iron, and these electrons go attack the H. These electrons move in here, and what does this all give? It gives those two products, and it reforms what? It reforms your FeBr3, which is your catalyst, and so catalyst is reformed. And you can maybe do this other ways. You can maybe just have these electrons take it. You could have something like BRH, plus and minus, and then this just leaves and become HBr. You might could do that also. This is probably textbook. And so here's where we remove the H, put in the double bond, we restore the aromaticity. It's just upside down. This is flip. Okay? And we get bromobenzene. Two-step. Sigma complex, and then the fast beta elimination. You can do the same exact reaction with chlorine. Like I said, you probably want to use FeCl3 so you don't scramble your halogens. You can also use the aluminum, like aluminum tribromide or aluminum trichloride, analogous to using the iron there. You can actually also use either iron or aluminum metal. Okay? If that was just iron, the iron will react with the bromine to form your Lewis acid. Okay? And theoretically, you only need like one molecule of catalyst. But you probably get a little bit more. So in that case, this is actually called a pre-catalyst. And it has to react with your reagent that's there to form the actual catalyst. So in the old days, when someone wanted to brominate, they would just like throw in like a nail or something, an iron nail, put it in there, and so some of the iron from the nail will react with the bromine. You'll get some FeBr3.
If you were chlorinating, wouldn't your solvent be insoluble?
What solvent? Or
So, for
we're not
example,
using the solvent here.
Okay. So it's just solid on solid, or
Well, chlorine's a gas, bromine's a liquid.
yeah.
You might want to ask what solvent would you use here?
Okay, because I was thinking, for example, like aluminum chloride. Actually, maybe that is soluble. Never mind.
Aluminum trichloride is a solid. Soluble in what then? What solvents would you use?
I guess ethanol, maybe.
I'm not showing any solvent here.
Okay.
Probably wouldn't want to use ethanol. Ethanol is going to react with bromine. Acetic acid is a common solvent. Some like dichloromethane, chloroform, those might be reasonable solvents.
So would you just bubble it through as a gas?
The chlorine?
Yeah.
Yeah.
Okay.
Or you can buy it already in solution, like chlorine and acetic acid you can probably buy.
Okay.
There are some alternatives though. For example, when you guys, some of you chlorinated last week, you didn't use chlorine gas, did you? What did you use? NCX. So there's a number of alternatives. This is the classical. Using the halogen is the classical, which we're going to be covering, and which you'll see in the textbook. In practice, there are a number of unique alternatives. Okay, what about iodine? Well, iodine is not that reactive. Even complexing the iodine with the Lewis acid, it still doesn't work. With iodine, you need to actually form I+. Note that above, we did not form that. Now, we formed a complex that had a positive bromine, but it wasn't just Br+. Because the complex, the bromine had an octet. That would not have an octet. But to get iodination to work, you typically need to form I+. How do you form I+ from iodine, the molecular halogen? Well, the oxidation state here is 0. I+ would be a +1, so that's an oxidant. You need to oxidize the iodine with an oxidant. Common oxidants are copper 2 chloride, which would be called cupric chloride. Y'all cover cuprous, us-ic? No, yes? Y'all cover us-ic? In Gen Chem? Yep. Okay. So this would be cupric chloride. Cupric chloride. Copper 2 is an oxidant, a mild oxidant. Hydrogen peroxide. What is that? We've used that before.
Proiodic acid.
Proiodic acid. Those are common oxidants that can be used with iodine. And what does this generate? It generates I+, okay? And I+ is your electrophile just like an E+. So once you form your I+, just refer to your generic mechanism, okay? And replace E with I, and there you go. Questions? Okay. What about fluorine? Fluorine, on the other hand, is so dang reactive that you typically need to stand back.
Yeah.
Okay? So reactive, you don't need a Lewis acid, you don't need a catalyst. Just fluorine is probably, it's likely to go boom.
Yeah.
Okay? Very exothermic, because the CF bonds are so strong, when you make them, it's just so lower in energy. So we typically do not cover a direct fluorination using F2. Later on, we'll see that using diazonium chemistry, that's a classical way to get a fluorine on the ring. Diazonium chemistry. And so in about a week or so, I'll refer you back to this right there. I'll say, remember when I told you that? And you'll say, yeah. Okay. Now, there are some unique reagents. For example, I've used a lot of these so-called NF reagents, where the fluorine is on a positive nitrogen. And so the ring can attack the fluorine and kick off the positive nitrogen. These are actually reactive enough. The nitrogen's a decent leaving group, and you can fluorinate.
Quick question. For the I+, once the double bond attacks, what would be the, I guess, factor that attacks the hydrogen for the beta elimination?
Well, we didn't balance this. I mean, the copper is going to go down to probably copper 1. And so you can say copper chloride, because only one Cl is going to sit there. And so you got another Cl minus that's, maybe it could pick it up. So you make something like HCl. That's the fate of the other chlorine, since this is now copper 1 because it got reduced. So there's something going to be around. Okay, so that's halogenation. And everybody halogenated sulfanilamide last week. I think most of you actually dihalogenated sulfanilamide. So you just twice the fun, right? Okay. You do one mechanism, then you repeat, you put a second one on. Okay. Now, in the guidelines to the report, I told you you can just use, I think, instead of using the specialized reagents, I told you I think you could just use like the elemental halogens for your mechanism, just like we did right there. Okay. All right. Next reaction. By the way, where are all of our reactions at? Pink sheet, set back to the first page. So we just did halogenation. Let's look at nitration. There's also letters here. And the pink sheet also has the letters, halogenation. Did we look at each of those topics? Now we're looking at nitration, and what's the first thing under nitration? Formation of the nitronium ion. Yes, there it is, the nitronium ion. How do you form it? Typically from nitric acid. Okay, the E plus is this guy's. First off, your nitro group, this is your Lewis structure with the ring attached here. Okay, it's always going to have the two charges. Make sure you know your nitro structure. Of course, that's a resonance structure that your hybrid would have some sort of delocalized electrons through there. This is called the nitronium ion. It's typically formed from nitric acid. Okay? First off, nitric acid Lewis structure. Nitric acid, you learned in Gen Chem, right? How can we get from here to here? First off, what do we need to lose? What do we need to lose to get to NO2? An OH. So OH has to leave. How you make OH a better leaving group? Why do you think we need acid? Protonated. Yes. Okay. This gets protonated. And we end up with okay. Now, what's odd about this? This is a pretty strong acid. We're protonating a pretty strong acid. First off, what type of acid would you use for this? Give me an example.
Strong acid.
H2SO4.
HF.
H2SO4.
H2SO4 is most common. Okay. You could possibly do it with other strong acids. Just like you protonated an alcohol, what acid would you use? HF could possibly work, but it's expensive and just, it works on tests, but it's kind of expensive.
Couldn't you just use HNO3 and like have a mechanism that's akin to like propagation of radicals, so that like after you protonate it, it just continues on like that?
I like your first statement, but then you got radical.
I mean, it's a similar to like propagation step of the radical, where you just.
Well, here's what I thought you were going to say. Okay. Actually, nitric acid can protonate itself. Okay. So sometimes you may not need sulfuric acid. You can actually have nitric acid protonating itself. I thought that's what you're going to say. This could be sulfuric acid. It can also be nitric acid, because one molecule of nitric acid can protonate another molecule. There you go. Once you protonate it, what do we need to do?
Just make the water leave.
This needs to leave. Now you can do it two different ways. I typically would do it all at once, but I'm going to do it like this because this will reinforce something. Have we ever said this? Anytime you can make a pi bond and kick off a leaving group, that's easy to do?
Yep.
Okay, what does that give?
The nitrogen.
NO2 plus
That gives that. Yes, it does. And what did we kick off? Yes, there you go. And the minus that's going to sit with this would be the minus that's set with the H+. Like sulfite, or I mean bisulfate or something. Okay? There you go. Because yes, the nitrogen would still be positive, we protonate and we lose water. Dehydration of nitric acid leads to the nitronium ion. That's your electrophile. Okay? I'll redraw it here closer to our ring. Once you get it formed, then these electrons attack the nitrogen. But something has to leave the nitrogen because it can't have more than 8 electrons around it. So one of the pi bonds moves over to the oxygen. Either one's the same thing. What does that give? It's going to be upside down again, but we made a bond to N. One double bond to O is still there, but the other one, the electrons moved on to the oxygen. Okay, minus. The nitrogen is still positive. Positive charge here. There's an H there. There's an H on every carbon. There's an H there. There's your sigma complex. Then something takes the H. Well, there's a minus somewhere. There's a minus sitting here. There's a minus sitting with this. What is it? Maybe HSO4 minus. And this guy takes the H. These electrons move in. All right. You get your double bond. Your NO2 group is there. And right here we reform what? We reform our acid catalyst. The H plus is actually catalyst. Nitric acid is going to be consumed. So, you have to know how you make your electrophile. Once you get your electrophile made, then it's your good old two-step mechanism, understanding the little structure of the nitro group that you've added. And then the last step is reforming the aromatic by the fast beta elimination. That's called the nitronium ion. Later on, we'll see something called the nitroso ion. This is nitronium. Questions?
You said that the nitrate could initially protonate itself, but then nitric acid can burn itself. If that's the case, then what would be the acid catalyst?
Well, one molecule of the nitric acid would actually be serving as a catalyst.
Would it be the oxygen or the nitrate?
There's no oxidant here.
Or the oxygen has a nitrogen that would be the one that takes the nitrogen?
Do what now?
What would be the atom that takes the proton when it has to deprotonate?
Right there. That oxygen takes the proton. The proton is, there's a sick proton. Write it out and show me.
In the last step, where the HSO4 is taking the H, if you are just using the HNO3, would it be the negatively charged oxygen that's taking the H to eliminate it?
Yeah, whatever acid you use, the conjugate base, you could show taking the H. If I use nitric acid as the acid, then NO3 minus could take the H. If I use phosphoric acid, then H, whatever, PO4 would take the H.
Before you were
Marvin?
why does the stable aromatic ring want to react with the nitronium? Like, it just doesn't seem like it makes sense.
Why does benzene react with the nitronium?
Yeah, because it's very stable and it doesn't actually. I mean, I get that there's no net charge at the end and there was when you started, but
Why didn't you ask that about bromination?
because that made sense to me.
Well, nitronium ion is very electrophilic. I mean, it seems like you could ask the same question for any. Yes, these are delocalized electrons, but they will react. How easily? This reaction still may require some heat. If this was an alkene, it wouldn't require any heat. It's going to react very fast. This is slower, but it still will react in a lot of the reactions. There's some it won't, and we showed that on day 1. For example, benzene will not react with KMNO4, where a regular alkene will. So just what you don't know is how reactive is the nitronium ion. I'm telling you, it's pretty darn reactive. It's pretty electrophilic. Now we're also using benzene here. If we use substituted benzenes like anisole, everybody know what anisole is? Anisole tends to be much more reactive than benzene, and we'll get to that. Okay. Now once you get a nitro on, as we said earlier, it's a common precursor to your amino. Because the nitro, these oxygens can be reduced off. Okay? It's a reduction. Two ways. We're removing oxygen, so it's a reduction. We're adding H's, so it's a reduction. So the nitro group can be reduced. One of the most common ways is to use an active metal with acid. Active metals include iron, tin, or zinc. And actually next week, this is what you'll be doing in the lab. You'll be reducing your nitrofluorine product to the aminofluorine product using, there's actually a choice. I think it's two choices. I think it's either zinc or tin. Your choice. Acid, sulfuric acid, you can even use like hydrochloric acid. Sometimes acetic acid is acidic enough. Another way to do this is with hydrogenation. Hydrogen in a precious metal catalyst such as palladium or nickel. These are the same conditions that we reduced alkenes, like an alkyne to an alkene, alkyne to an alkane, or an alkene to an alkane. Hydrogenation will also convert this to this. Now there we're not going to look at a mechanism. Okay? But it is a routine reaction. And in the research lab, whenever we reduce nitro groups, we commonly use hydrogenation. Okay? And I don't have it queued up here, but I may. I just want to see if this shows up. You see this? That's an orange solid in a bottle. Can you see that? Can y'all see the orange solid? It's sort of spread out in the bottle. Okay. This is a septum. You can't see the gas line. It's there. I'll show other pictures. This is a nitro compound in a bottle, and the hydrogen gas is going in. There's a picture of the apparatus. Okay, here's the same bottle. This is a tank of hydrogen. It's fed by a bigger tank that's on the other side of the counter, way over there. There's a line coming in. Hydrogen tank. This is a motor. And this thing here is on a shaker, so instead of stirring, you shake. That shows the gas. This knob is where you enter the gas into your bottle. This shows your gas pressure, hydrogen. This is where you turn it on, and see it shaking. You don't use a stir bar, you just shake. And there's hydrogen in there. You see the line up here, this plastic tubing coming in here. These bolts you clamp down tight so it can be under pressure and the top doesn't pop off. That's called a hydrogenator. And that's doing this reaction here with hydrogen to the amino group. Check the pressure. There's the reaction after like about an hour. What do you notice? The solid is no longer present. It's starting to dissolve. There's the reaction when it's done. What do you notice?
It's blue.
The orange yellow is gone. Okay. It looks blackish. That's because that's just the catalyst that's floating in there. When it's removed and that's filtered, it's a near colorless to pale kind of bluish solution, but everything's dissolved now because the amino group is much more soluble. And when it's formed, it all dissolves.
So do you have heavy metal cations inside of the solution already, or
Have what?
heavy metal cations like the palladium or nickel?
Well, palladium is a metal.
Okay.
And the palladium, you remember palladium on carbon?
Okay.
It's dispersed on charcoal. And what color is charcoal?
Black.
That's why it looks kind of dark, and it's dispersed. The charcoal helps disperse it because if you just put a wee bit of palladium in there, it would just sit at the bottom and it wouldn't have a good surface area. Okay, so hydrogenation, but in lab we're going to use the active metals. It's also called a dissolving metal reduction because the metals will dissolve. Okay, one thing to keep in mind, these metals will react with acid to produce hydrogen. Okay, this is a common reaction. That doesn't mean that hydrogen is produced and hydrogen reduces the nitro group. I'm just reminding you of this chemistry. And actually, if you want to produce hydrogen in the lab, this is a common way to do it. You treat like iron with like sulfuric acid, and it'll generate hydrogen. Okay. So that's the two-step sequence of nitration followed by reduction to give your amino group. Next reaction for aromatics, sulfonation. You can react benzene or benzene derivatives with sulfur trioxide, sulfuric acid, catalyst. We can get the SO3H, which is a benzene, this is a sulfonic acid. Sulfonic acid. It was not on our functional group list. There's your Lewis structure. It's a sulfonic acid. We may have seen tosyl acid. We've seen tosyl chloride. If you replace the CO with an OH, you'll have tosyl acid. We'll maybe use tosyl acid later in the semester. It's a benzene sulfonic acid. They're made by this reaction here. What's our electrophile? If we draw a Lewis structure for SO3, you can do all triple bonds. We do all triple bonds. What do we have around sulfur? 1, 2, 3, 4, 5, 6 electrons around sulfur? Or what's the charge of sulfur here? It's neutral. You could do this. The only thing you have here is dipoles. Okay, the sulfur is not extremely electrophilic. But if we protonate one of the oxygens, I assume you can protonate, then we can draw maybe resonance. We do have a stronger dipole here. We can actually draw a resonance structure maybe. The resonance structure would have that there, but now the positive is on sulfur. Protonation of the oxygen makes the sulfur more electrophilic. We can see that by showing a resonance structure. So now the benzene will react with the sulfur. You don't have to move any electrons. So you get the benzene bound to the sulfur, but we have double bond to O, and OH. There's an H here, there's a positive charge here. There's your sigma complex. And so now we use something to pick up the H and do the fast beta elimination. We give our sulfonic acid and we reform our H2SO4. So this is your catalyst here. And protonation of the SO3 makes it more electrophilic. Okay. One thing we can say about sulfonation is that reaction is reversible. For example, you can take benzene sulfonic acid, heat it with an acid catalyst, and you can regenerate benzene. You can go backwards and give off SO3. Okay? How would you go backwards? If something is said to be reversible, that means the mechanism, every step is reversible. That is, you can go back to here, and you can go back to here, then you can go back to there. Okay? So you might look at this and do it in reverse as practice. Just do it in reverse, but act like you're going forwards. So this would react with what? You'd need to get an H plus on the ring. That would give you your first intermediate going backwards. So try to work that. See how we do on that. In that particular case, the SO3 can sometimes be used as what's called a protecting group. A protecting group is where sometimes a group is put on the ring, and then you do something else, and then you later remove that group. Okay, as we finish up here, just a drug example. Here's an amino group on a benzene ring. What's the most common? How do you get an amino group on a benzene ring? Two-step process. You first
Nitro,
nitrate
and
and reduce.
yeah.
That's most likely how that drug here was made. By the way, if you remove the amino group, if there's no amino group there, anybody know the name of the compound if there was no amino group?
Thalidomide?
Thalidomide. Yes. It's thalidomide, which caused birth defects back in the 1960s. Yes. Well, they put an amino group on thalidomide, and now the new structure is used to treat some type of cancers. Next time we'll be looking at substituent effects. That is, what if you had toluene? What if you were brominating toluene? Where would the bromine go compared to the methyl? Where did the new groups go compared to the existing groups? So we'll be looking at directing effects, activating effects, etc. Please be looking ahead. Everything should be outlined on the pink sheet. Pink sheet outline. Okay, we'll meet upstairs. Upstairs in lab